Alrighty, children, we've got another day of application problems here with the trigonometries, which is so exciting, you know, doing the study of right triangles. Let's get to it. Let's hop to it. Let's dive in to the math. Alright, so according to the parking standards in Huntley, an access ramp to a parking lot cannot have a slope exceeding 8 degrees. All right, so it's like an 8-degree pitch of that ramp, the access ramp. Suppose a parking lot is 12 feet above the road. If the length of the ramp, the slope part, is 70 feet, does this access ramp meet the requirements of the code? Explain by showing the math problem. Okay, I'm going to make this a little smaller so we have room to work. Okay. So we've got a parking lot that's 12 feet above the road, and the length of the ramp is 70 feet. I'm going to draw that out, right? So I've got the normal road, right? Then the parking lot is 12 feet above, right? And then, we're in the parking lot. So this is 12 feet. Now, the sloped part of the ramp, this part, is 70 feet. That's what it said there, right? The sloped part. Okay, and then, you know, you got your normal road or whatever, continues on out here. Let me try and connect that. That's a little better. Okay, so there's my access ramp, right? And I want to make sure that we don't have a slope that exceeds 8 degrees. So this guy right here is my angle, theta we'll call it, and I want to see if that's bigger or smaller than 8 degrees, right? So basically, I could solve for the angle and see what my answer is, right? And that would tell me whether or not it works. Well, that's my angle there. What's my 12-foot side? That is my opposite side when we're talking about its relation to the angle, right? So from that angle, that is the opposite side, because this is a right angle right here, right? And then this is my hypotenuse. Okay, so across from that angle is my opposite. Across from the right angle is always my hypotenuse. It's the opposite and the adjacent that change. So if I have opposite and I have hypotenuse, what am I using? Well, why don't we write out our so, ka, toa, boom. Well, obviously, if we've got the opposite and the hypotenuse, woo! So, all right, so we're going to use our sine. So sine of my angle is equal to my opposite over my hypotenuse. Or better yet, remember yesterday we said, hey, if we're solving for an angle, we can just use inverse trig. The math behind it would be taking the inverse sine of each side, or if you want your initial setup to just be this, if you're like, hey man, I'm solving for an angle, just pop it in the inverse, we're ready to rock and roll, that is going to give me my angle right there, okay? As far as traditional mathy-math setup, the one in blue there, and then taking the sine inverse of each side, we'd go like sine inverse on each side, and get to where we want to be. Okay, whoop, -1, sine, okay. So we take the sine inverse of each side, but really we could just set it up like I did in the green and be ready to rock and roll. So I get, let's see here, if I take the sine inverse of that, I get 9.87 degrees. And something I forgot to mention in the last video, if you're getting some funky answers, like if this is not coming out right, your calculator may be in radian mode. We should be in degree mode because we're looking for degrees, we're using degrees. Radians are a different type of measurement. They still have their purpose, but right now we should be in degree mode. So if you're using your TI-84, hit the mode button and scroll down a few lines and you will see either degree or radian highlighted, okay? So if you're getting weird answers, that is likely why. Okay, so is this thing cool? No. So it does not meet code or the requirements. And our reason is because it's bigger than 8 degrees, all right? So something's got to change. We got to, you know, length. Well, obviously this right here is that's gonna be fixed, right? So I got to increase that length in order for that degree measure to decrease, right? I got to take this ramp and make it a little bit longer if I want that angle to be a little bit smaller and meet that 8-degree code. Okay, awesome. So in a nutshell here, our answer is it does not meet the code, and there was our work in green to show that. All right. So you want to cut down a large tree on your lot to make room for a swing set. Standing 50 feet from the tree, so you're standing 50 feet from the tree, you use your Swanson speed square and a plumb bob, or you could use your phone, which has a wonderful like level with degree measures and everything. You find the angle of elevation of 65 degrees. So really, boom, that's what we're looking at, the 65 degrees right there. You're standing 50 feet from it. All right. You want the tree to fall towards your house because it is against a fence that backs up to your neighbor's yard. So you don't want it to fall the other direction. You want it to fall towards the house, otherwise it'll destroy your fence. All right. Your house is 80 feet from the tree. Oop. Is there enough room to cut this tree down? Explain how you determine your answer. Okay, so let's shrink this up a bit, make ourselves a little bit of room to draw our diagram. All right. So we've got this tree, and we're standing 50 feet from it. Let's see if we've got a brown marker that I could use. All right, I found one. So we got our tree. Whee! And I believe that tree will be rather lush. Maybe it's springtime, right? Yay! Okay. So you are standing 50 feet from the tree. So here's our grass, right? Whee! Okay. So you're standing 50 feet from the tree. We'll draw you. All right, there we go. And you see the angle of elevation of 65 degrees, okay? Now, just for ease of this problem, keep things a little bit more simple, I'm just going to draw, first off, we're going to use a triangle, so I'm going to go through the center of the tree up to the top, all the way up there, and then I'm going to come down, and we'll go right to the center of you, okay? And we'll do it to the ground so we don't have to account for the person's height. But in real life, you would have to account for your eye level. Like, say your eyes are 5 feet or 6 feet above the ground, you'd have to account for that. But we'll just go from the ground. Ooh, that was a lovely voice crack. I'm going to keep that in there. So you'll have to go from the ground. In this case, we'll just keep things a little simpler. All right. So we've created this right triangle, and we said this is 65 degrees. Again, it all comes down to triangles, guys. All right, it all comes down to triangles with this stuff. You're setting things up with triangles. It happens all the time in geometry. So when in doubt, triangle it out, right? Ooh, that was good. So we have a fence over here, right? So we don't want it to hit this area right here because there's a fence chilling right there. So we want it to fall towards us, towards the house. But there's a house. Your house is right over here, right? And that's 80 feet. 80 feet away. So is it going to, when it topples over, is it going to crash into the house, or is it going to be okay? Well, we got to figure that out, right? I don't want to test that out while we're in action here, okay? So what are we actually looking for? Well, I would believe we are looking for the height of our tree in this case, right? So we want to know what this is, because when it falls over, that's when it falls, that this right here, this vertical length right now is finna going to be on the ground, right? So we want to know our height of the tree before it falls. All right. And if you're wondering, well, how do you know which way the tree's going to fall? There's ways to do it. You tie a rope, pull it that way. As you cut it, there's the professionals, you know. All right. Let's set this bad boy up. So I know with this angle right here, 65, 50 is my adjacent side, right? It's next to the angle, and across from that angle, or opposite that angle, is the one that I want to know. So opposite, adjacent, that is my TOA. Alrighty, so tangent of 65 is equal to my opposite over my adjacent. So when I solve this bad boy, I'm just going to multiply by 50 real quick. And I'm going to get x equals, I'm going to get 107.2253, so 0.25. 107 and a quarter foot, so 107 and 3 inches, 107 feet and 3 inches. Well, is that going to be okay? Going to hit the house. No bueno. All right. But good thing we mathed it out first, so now we got to figure out another plan for this thing. So, I'm sure they'll maybe they'll chop the top off or something like that, and then they'll chop again. I don't know. But we know, as it sits right now, it's not going to have enough room to fall towards the house and away from the fence. All right, there we go. Good thing we mathed it out. Otherwise, it'd be a disaster. Okay, we got the base of Mr. Allen's favorite sled hill has an elevation of 740 feet above sea level and a peak elevation of 830 feet above sea level. If the length of the run of the sled hill is 410 feet, what is the angle of elevation, angle of depression? Okay? Now, one thing you'll notice is that the angle of elevation, the angle of depression are actually the same thing. They're just observed from a different point. And we'll talk about that with this problem. All right, this is actually real. I went on the Google machine, right, and searched my favorite sled hill, which we call Barberry. It's the neighborhood that is in Fox River Grove. Or Picnic Grove is what they call it, but we would call it Barberry back in the day. All right, so I'm going to draw this thing. We've got our base of our sled hill. I'm actually just going to draw a flat line, right? So this is going to be at 740 feet above sea level. And then the top of the hill is at, and I'm just going to make this into a triangle, so the top comes like whoop. Now all the way down. This is at 830 feet. Okay. So you got 740 feet and 830 feet. Those are my elevations, right? And then I know that the run of the hill is 410 feet. All right. So we measured that. Okay. Well, I want to know, what is my angle of elevation or my angle of depression? Well, my angle of elevation would be right here. My angle of depression is observed with a line drawn parallel. And then this angle right here, that is my angle of depression. How do I know that these two angles are the same thing? Well, that red dashed line I just put in, and this line down here, these guys are parallel, so these two are alternate interior angles. And if they are parallel, then the alternate interior angles are congruent. Okay, so finding my angle of elevation is the same as finding the angle of depression. All right. Well, how am I going to do this? Well, it looks like with the 830 and the 740, I've got 90 feet right here. Okay, it's got 90 feet for that height right there. If I'm going from the two elevations that we have, so I've got myself a triangle with an opposite side over here, opposite. And I've got my hypotenuse, right, because this is going to be a right angle right here. I got my opposite and my hypotenuse. Well, which one is that? So I can set up a sine function to figure this out. What am I looking for? I'm looking for an angle. So I can just start with sine inverse of my opposite over my hypotenuse and plug that bad boy into my calculator. So when I do that, when I do my 90 over 410, with my sine inverse, I get 12.68 degrees. So that is the angle of elevation or angle of depression for this particular sled hill. I'll tell you what, it feels steeper than that, but maybe that is accurate. I think that it's accurate because I use the Google machine. All right, there we go. That was lovely. Not too bad. Again, they're wordy problems as they are word problems. But they are set in a wonderful setting there, a nice little bit of application. You guys are always wondering, hey, when am I going to use this stuff? Well, right here, dog, when you decide you want to figure out the angle of elevation of your sled hill. You know what I'm saying? Woo! All right. I just read over my directions again. It said round to the nearest degree. What would that mean? That would mean it is 13 degrees. About 13 degrees then if we're doing to the nearest degree. Got to round up. All right, the last problem of the day here, guys. Find the perimeter of the isosceles trapezoid below to the nearest integer. This is a good like ACT type problem. I know you guys are taking the SAT these days, but you may end up wanting to take the ACT, and they'll throw random things like this on there. All right, so find the perimeter. And we're going to round to the nearest integer, which means we're going to be using our calculators. It's not going to be exact answers. We are rounding. But I like to go by the my life motto of YORO. You only round once. So don't round along the way. It will mess things up. Okay. Find the perimeter of the isosceles trap. Well, when I have trapezoids, I like to drop down altitudes because it creates right triangles and a rectangle, right? So that means that this side right here is 10, and if the whole thing was 20, then I'm left over with 5 and 5. It's isosceles, right? Which means the legs are the same, the base angles are the same. Okay, so that means that this is 70. So if I figure out this side right here, it's the same as this side over here. Okay, so there's really only one task that I have at hand at this point. So let's solve that triangle. Well, I know, and I'm going to use a different color marker here, I know that my 5, with respect to this 70-degree angle, the 5 is my adjacent side, the x is my hypotenuse, right? Indeed. All right, I'm looking at it from the perspective of that 70-degree angle. So I can set up what trig function? Ka. So ka, toa. Cosine in this case. Alrighty, so cosine of 70 degrees is equal to my adjacent side, 5, over my hypotenuse, we'll call it x. Now I got to solve. So I'm going to multiply by x on both sides. So I get x times the cosine of 70 is equal to 5. Now I know that cosine of 70 is just a number, okay? Not that I'll plug it in right now, but if I were to, it's 0.34202014332566. It goes on forever. All right, so it's just a number. Well, how do I get x by itself if that's just a number? I got to divide by it on both sides. So in my calculator, equals 5 divided by cosine of 70. And then at that point, we will round. So don't do cosine of 70. Remember, cosine of 70 was, again, 0.3420, blah, 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 blah. You wouldn't do 5 divided by 0.34 because then you're going to be a little bit off. So if I plug it all in once in my calculator, I get 14.619022, blah, 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 right? And I'm just going to write this down for now, but we're not going to use this. So 619022, right? It goes on forever. That's what I'd get for that side. Now it says, find the perimeter of the isosceles trapezoid below to the nearest integer. Well, I don't want to round this to the nearest integer and then continue on. That would give me a slightly different answer. So how many of these sides are there that we just found? There's 2 of them. So I'm going to multiply this number by 2, right? So I'm going to multiply by 2, and then I got to add in the 2 other sides, the plus the 10 and plus the 20, plus 10 and plus 20. So we're adding those in, and I get, as my final answer, 59.238, so on and so forth, which is 59. All right, that is to the nearest integer for my final answer, okay? Now, say I were to have rounded along the way. What if I were to have rounded this guy to the nearest integer and called it 15? If I did 15 plus 15, and then the 10 and the 20, I'd be getting 60 for my answer. That is incorrect. So again, yo-ro, you only round once. Wait till the very end to do that. So keep those numbers in your calculator. Keep multiplying in there. The arrows on your TI 83 or 84 are very helpful. You can arrow up and grab old numbers and things like that and use them so there isn't the rounding that's going on. All right? Nice work on this one. Actually, I don't know that because I can't see what you're doing, but I know I did a nice job, I think. All right? Lovely. Homework, dogs. Only 5 questions, which is nice.